Hey guys, we'll start today's lesson off with the bell ringer. You're going to solve the inequality 3x plus 5 times the quantity of x minus 1 is greater than 2x minus 3. Remember, when you're solving an inequality, solve it just like a normal equation. So go ahead, pause video, solve the bell ringer, and then unpause it for your solution. So your solution should be x is greater than 1/3. We're going to start today off by talking about interval notation. Now, interval notation is another way of writing an inequality. So if we have the open interval, AB, notice it has parentheses. It represents the real numbers between, but not including A and B. So it's all the numbers between A and B, but without A and B in it. And then we have the closed interval using brackets, represents the set of real numbers between and including A and B. So A and B, when we use brackets, are in the solution, and then we have everything in between. And also we have set builder notation introduced here. So this right here is set builder notation, specifically this part. And all you do is use brackets, and then you present the variable, you define the variable x, and then you give the stipulation. So in this case, it's between A is less than X is less than B. And notice when we have the brackets here, we have less than or equal to signs here. Now we also have the infinite interval notation. So that's whenever we're talking about the X is greater than a number or X is less than a number. So if if X is greater than a number, say that number is A, we say that is between A and infinity. Notice that with infinity, we have a parenthesis because you cannot be equal to infinity. So we use a parenthesis. And if we want X is less than a number, so B, X is less than a number B, it can be any number less than B all the way down to negative infinity. And again, we have a parenthesis because we cannot be equal to the negative infinity. So we're going to get some practice on using this notation. Now this slide just shows us some specific interval notation. So looking at the first one, we have A and B both not included, and it gives us the set builder notation and the graph. Now looking at the graphs, they use brackets and parentheses. We're used to using the open circles for not including and the closed circles for including. So we're going to continue to use that, but this is also an acceptable form. So this slide's just for a reference if you can't remember how to write something in set builder notation or to interval what the graphs look like, you can just take a look at this. So now we're going to express the interval in set builder notation, and we're going to graph it. So in set builder notation, the first thing you do is you start with a bracket. And then you define what your variable is going to be. So we're going to use x. And then you throw a little bar in there. And then you write the inequality that we'll have for this interval. Well, x is going to be between -3 and 2. So it needs to be just greater than -3, but less than or equal to 2. And I know it's greater than just a greater than with a -3 because we have just a parenthesis. And I know that it's less than or equal to the 2 because of the bracket. And now to graph this, I know I have a point at -3, and it is open because of the parenthesis, and a point at 2, and it is closed because of the bracket, and I will be everywhere in between. The next one is 0 and 4, including both. So my set builder notation will be used with x, for which 0 is less than or equal to x, which is less than or equal to 4. So I know I have points at 0 and 4, and because they're both brackets, they will be closed points, and I will have everything in between. The next one we have negative infinity and 2, both excluding. So when I write my set builder notation, still use x, for which, now to think about this, x is between negative infinity and 2. That means it's going to be any number less than 2. So my inequality is x is less than 2. And I know I have an open point at 2, and I go down to negative infinity, so down forever. So now I want you to do a couple by yourselves. Go ahead, write the set builder notation, then graph it. So pause your video now, and then when you're ready for the solution, unpause it. So here are solutions to the huddle. If you need to, go ahead and pause the video to check your solutions, and when you're ready to go, unpause it. Now we're going to graph intersections and unions of intervals. And to find intersection unions of two intervals, first you need to do is graph each interval on a number line. And if we're talking about intersections, that's going to be using this symbol, which is an and symbol. That'll tell us we're looking for an intersection. To find an intersection, take the portion of the number line that the two graphs have in common. You're going to see exactly what that means in the next slide. And to find the union, so that'll be with a U or an OR, take the portion of the number line representing the total collection of numbers in the two graphs. So let's get a solid look at some examples of what those are. So here we have the graph of 1 to 4, not including 1 or 4. And notice there are parentheses at the 1 and the 4. And then we have the graph of 2 to 8, including both. And we're finding the intersection of both. So that is where they overlap. So if we were to take each of these graphs, put them on one number line, it's where they would overlap. And that is in the third graph. So you would say that this is the intersection of 1 to 4 and 2 to 8. So therefore it is 2 to 4 including 2 and excluding 4. Here we have a union of intervals. Same intervals, 1 to 4 and 2 to 8. But this time, since we're working with a union, it is both of the lines combined. So it's like if we graphed both on the same number line and use the entire number line. So it's where they overlap and where each of them are. So the union of these two intervals is 1 to 8, excluding 1 and including 8. So let's go ahead and do one ourselves. We're doing negative 2 to 3, excluding negative 2 and including 3. And the union with that with 0 to 4, including 0, excluding 4. So let's go ahead and graph each interval. I will have an open point at negative 2 and a closed point at 3. So there's our first one. And then the second one, I'll have a closed point at 0 and an open point at 4. Now, since I'm looking for the union of these, I just smush the graphs together and it'll be both of them combined. So that means I will be going from negative 2 up to 4. So the union of these two intervals is negative 2 to 4, excluding both. Here we have an intersection of the same intervals. So we're going to have the same graphs. We'll have again, an open circle at -2, closed at 3, and a closed circle at 0, open at 4. Now this time we're taking the intersection. So that's where they overlap. So looking at the two graphs, notice that the second one does not have the -2 to 0. So we're not going to include anything before 0. So 0 is going to be our lowest point because both graphs have to have those values. And then we can go all the way up to 3, and we're going to have to stop because in the first graph, the 3 doesn't have the 3 to the 4. So the overlapping is from 0 to 3. So the intersection of the two intervals is 0 to 3, including both. So go ahead by yourself and work through this intersection. You're going to find the intersection from 1 to 3, including both, and 2 to 6, excluding both. So go ahead, pause the video, and when you're ready for the solution, unpause it. So here is the solution to the intersection. It'll be 2 to 3, excluding 2 and including 3. So now go ahead and do the same thing for this one. This time we're doing the union. Go ahead and pause the video. When you're ready for the solution, unpause it. So the intersection of the two graphs will be 1 to 6, including 1 and excluding 6. So now we're going to get into solving some linear inequalities. We solved one for the bell ringer, but looking at this one, it's going to be a little different. So let's go ahead and start solving this inequality for x. So the first thing I have to do is subtract 7 from both sides, and I'm going to get -x is less than or equal to -7. And then to get x alone, I'm going to have to divide both sides by -1. So I'll be left with an x on the left side and a 7 on the right. Now remember, when we divide by a negative number, when working with inequalities, we have to flip the symbol. So instead of being less than or equal to, it is now a greater than or equal to. So when we multiply or divide both sides of an inequality by a negative number, the direction of the inequality symbol is reversed. You have to remember that. So with our equations, there are some properties. We also have properties with inequalities. So we can add or subtract something to both sides of an inequality and it'd be true. And with positive numbers, you can multiply or divide positive numbers to both sides of an inequality and have it not change. But whenever you do work with negatives, multiplying or divided, that's whenever you have to flip your symbol. So only when you're multiplying or dividing by a negative number is when you have to flip your symbol. So let's go ahead and solve this inequality. 4x minus 5 is greater than or equal to x plus 7. We have variables on both sides, so we have to get them on the same side. So I'll do that by subtracting x from both sides. And I'll have 3x minus 5 is greater than or equal to 7. Then I have to get x alone, so I'll add 5 to both sides. I'll have 3x is greater than or equal to 12. Divide both sides by 3. Since it's positive, I do not have to flip my sign, so x is greater than or equal to 4. And if we want to, we can write this in interval notation. My lowest I can be is 4, including because it's an equal to, and I can go all the way up to infinity. Let's go ahead and graph this. We'll have a closed circle at 4, and I can be everything to the right of it. Alright, I want you guys to go ahead and do this one yourself. Make sure that if you are dividing by a negative number that you're flipping your sign. So go ahead, pause the video, and when you're ready for the solution, unpause it. So your final solution should be x is greater than or equal to -1. So here we have an inequality but this time we're working with fractions, so we have to get rid of all of our fractions. So we know how to do that. We just need to clear our fraction by multiplying the LCM of 2 and 3, which is 6. So I'm going to multiply my entire inequality by 6. So I'll have 6 times x plus 1 over 2 plus 6x over 3, and that'll be greater than or equal to 6 times 3x plus 2 all over 2. So I can do some simplifying. 6 over 2 is 3, so I have 3 times x plus 1. 6 over 3 is 2, so I have 2x. And that'll be greater than or equal to 6 over 2, which is 3, so 3 times 3x plus 2. Then I just solve this like a normal inequality. Got to do some distributive property. So 3x plus 3 plus 2x is greater than or equal to 9x plus 6. Get my variables on one side. After I do a little simplification, so I'll get 5x plus 3 is greater than 9x plus 6. I'll put my variables on the left side, so that means I'll have negative 4x is greater than or equal to, I'll put all my constants on the right, so 3. Divide both sides by negative 4, so we'll have to flip my sign, so x will be less than or equal to negative 3/4. So go ahead, I want you to do this one by yourselves, and when you're ready for the solution, go ahead and unpause the video. So the solution to this one is x is greater than or equal to 13. Now I just realized I made a mistake in this one. So go back to this slide. And when I multiplied by 6 in this second step, we should have 6 times 3 times x plus 2. That'll make a big difference. Instead, I'll have a 2 times 3 times x plus 2, making that a 6x plus 12. So I'll have to change that here as well. And that means I will have a negative 1x greater than or equal to 9. So then x will be less than or equal to 9. So, back on track, back to this problem. The second huddle one, go ahead, solve this one by clearing fractions. Again, when you're ready, unpause the video to get your solution. So here's the solution to the next one is 3 plus 2 is less than x. Now, there are some solutions when we're working with inequalities where we can get something that's called the null set. And then there is a solution where we could get a set that's all real numbers. So we have one of these, each of these situations here shown. So let's do x is greater than x plus 1. Well, we need to get our variables on the same side. So subtract x from both sides, and we get 0 is greater than 1. Now, 0 is greater than 1 is a false statement. And since it is false, we say that it is the null set, or that there is no solution. Because there's nothing we can put in for x that'll be greater than 1 more than that. Looking at the other one, again, if we subtract x from both sides, we'll get 0 is less than 1, which is true. That's a true statement. So we say that that would be the set of all real numbers, so negative infinity to infinity, or the symbol for all real numbers. So everything we can put in for x would be a solution to this inequality. So let's take a look at an example. Let's solve this inequality. We have x minus 3 is less than x plus 4. If I add 3 to both sides, I'll get x is less than x plus 7. Subtract x from both sides, I will get 0 is less than 7, which is a true statement. So I will have negative infinity to infinity, or all real numbers, as my solution. Go ahead, work through this next one, see what you can get. When you're ready, unpause the video. So for this one, we got the solution 0 is greater than 7, and that is a false statement. So we have the null set, or no solution. So that'll get you set for your homework. For your homework, it's not going to be the same that is in the book. I'm sorry, in the packet. You're going to do page 126, and you're going to do problems 3 through 45, all of them. Just kidding. You're going to do multiples of 5. Alright, so that should get you started. Go ahead and get started on that, and then turn that in tomorrow as well as last night's homework.